Hi, welcome to Understanding Force Calibration Certificates. Here at Morehouse, our purpose is that we create a safer world by helping companies improve their force and torque measurements. My name is Henry Zumbrun. I've been the president of Morehouse since 2013. If you have any questions after this presentation or even during, please feel free to send me an email or give me a call, whatever your preferred contact method is. Morehouse, we are a manufacturing company that produces force calibration equipment and adapters that are used in industry to measure force. We have state-of-the-art force and torque calibration laboratory and offer calibrations at a very high level of accuracy. Often people talk about primary standards laboratories. That's what we have for both force and torque. We offer deadweight calibrations on primary standards up to 120,000 pounds of force, known to within 0.002%, and we other force calibrations up to 2.25 million pounds of force or 10 meganewton, known to within around 0.01% of applied force. Our agenda for this session is discussion on calibration certificates and ISO/IEC 17025 requirements. We're going to talk about single-run calibration certificates, specifically non-linearity, hysteresis, SEB, and resolution. We're going to talk about pass-fail statements of conformance and what that means and how to make some of those calculations. The participant will be able to have knowledgeable discussions of what is required on their certificate of calibration, the proper language to use, and understand the basic math behind some of the calculations. Some additional reading material here, if you have the PDF or if you want to go to our website, these can all be found. We have a technical paper called Recommended Compression and Tension Adapters, highly recommended paper. We here today are going to talk about calibration certificates, single run, pass, fail. That paper talks about the other part, the adapters, the interaction with things, how things interact. You could get everything right, have a 0.1, know your device to within 0.1%, use a different adapter and have a 0.5% error. An error 5 times larger, an error 17 times larger, an error 20 times larger, just by switching or using different adapters. So that paper, again, that's recommended compression and tension adapters. An additional paper on uncertainty propagation, if you're interested on how that works from primary to secondary to another, which we'll talk about in this. And then we have a technical paper on risk. We're going to talk later about TUR. And a lot of people say, hey, if I'm 4 to 1, that's good enough, right? And we're going to talk about why that's not enough. So first is understanding the requirements of ISO/IEC 17025:2017. And this is found in section 8.2. It's all of the things when a calibration report is issued, we have to follow these requirements. And the new one, or one that at least we missed, we had an audit and we had one deficiency, and that was we missed the date of issue of the report. We went over everything, and yet we still missed one thing, and that was it. So I've highlighted it. I think a lot of people probably think it's good enough to just say, hey, calibration and be done by, or the date of it, the date calibrated, and have that be enough. But the new standard requires some additional reporting. In addition to that, some standards and some things we're going to talk about. The measurement uncertainty result shall be presented. That should be on all certificates. Statement identifying how the measurements are metrologically traceable. Calibrations in this is not good. That's not metrologically traceable. And then we have 7843, a calibration certificate or calibration label shall not contain any recommendation on calibration interval, except where this has been agreed with the customer. So we can have these discussions between one another on calibrations and due dates. We often get asked, like, what do you recommend? And the answer is always going to be dependent on the risk tolerance for the company or individual. If you want to maintain a very, very tight tolerance, meaning, better than 0.01% of applied force, probably going to want to have your items calibrated, at least at a yearly interval. If you want to maintain, 0.1%, maybe that's longer. It all depends on the device. What I can say for certain is if you send your devices to a calibration laboratory, and they are constantly adjusting them. You should either purchase new equipment or you should shorten the calibration interval. It's one or the other, or both, maybe, depending on what you need to do and how critical the application. Though if they're just not meeting, shorten it. And on the flip side, if every time you send it to the lab, it's always in tolerance, maybe you can extend it out and save some money on calibration. There's two sides to that. And when we start talking about identifying, how measurements are metrologic traceable, we're talking about the International Vocabulary of Metrology, which is the VIM, which defines metrological traceability as the property of a measurement result whereby the result can be related to a reference through a documented, unbroken chain of calibrations, each contributing to the measurement uncertainty. Here we have what we're talking about. This is like a pyramid where the measurement uncertainty data is cumulative from one level of the hierarchy to the other. So when measuring force, the load cell should be calibrated using measurement standards traceable to the SI through a National Metrology Institute, recognized under the CIPM MRA. This recognition is necessary as some NMIs cannot provide traceability. And then we look at our own NMI here, NIST, and their website clearly states metrological traceability requires the establishment of an unbroken chain of calibrations to specified reference standards, typically national or international standards, in particular realizations of the measurement units of the International System of Units, SI. And that NIST assures the traceability to SI. The next tier in the pyramid is a primary reference laboratory. That's us. We're here. We're following this. First we start at, SI, then we go to an NMI. Here we're at the primary reference laboratory, which is Morehouse, where we have measurement uncertainties at one standard deviation of about 8 parts per million, or 0.0008%. And, our traceability is to SI units, and it's validated by NIST calibrations on our several deadweight force machines, and we provide our additional metrologically traceable force transducer calibrations. The NIST does the calibration for our force standards, our load cells, up to 1 million pounds and up to 2.25 million, or 4.4 meganewtons to 10 meganewtons. NIST does the calibrations on those load cells, and the one where we are going to 10 meganewton, NIST calibrates 3 load cells close to 1 million pounds to get there. Force is derived. It's a derived unit. The SI base units for force are mass, time, and length, as shown in this illustration. The formula for force is mass times acceleration. Using these base units, the VIPM defines 1 Newton as the force required to accelerate 1 kilogram to 1 meter per second in a vacuum. And we can see that right here, and we can see the kilograms per meter per second. So really nice chart that NIST has here. A statement identifying how. So remember we talked about traceable to NIST and how that's not good. It's essential to have a chain of traceability in which uncertainty is propagated correctly. That's the uncertainty propagation paper. However, traceability is not to NIST. No. When calibrating load cells, many laboratories fail to get the metrology aspects correct and improperly state NIST traceable master standards, or traceability to NIST, NIST traceable. Anything, any combination of it. At Morehouse, we have seen all sorts of incorrect uses of NIST traceability. So the next time you see NIST traceable statement, question it, as that statement is not correct. It would be best if you also ask how far away the lab was from NIST in regard to metrological traceability. Remember, we had that pyramid, and the further away one gets, the larger the uncertainty becomes. So someone could be 4, 5, 6, 7, 8, whatever it is away from this, where their uncertainty is very, very large. So you really need to look at the lab scope of accreditation and make the appropriate determination if that laboratory that you're choosing to send your equipment to has the capability to perform the calibrations as required and as you need. Because the one thing you cannot have, you cannot make a better measurement uncertainty-wise than the lab that performed the calibration on your references. You may be able to make the better measurement, but uncertainty and mathematically, it does not work. Every level down, the further you are away from SI, the larger the uncertainty becomes. And then we get into another thing. The measurement, talking about uncertainty, we should need to state the measurement uncertainty of measurement results presented in the same unit as the measurand or in a relative to the measurand. So here's a certificate we have, a load cell that's in tension. And it basically, we're reporting the measurement uncertainty, and we're doing this per ILAC P14 as we need to abide by ILAC P14 as part of our accreditation. And ILAC P14 section 5.4 states, contributions to the uncertainty stated on the calibration certificate shall include the relevant short-term contributions during the calibration and contributions that can reasonably be attributed to the customer's device. Can reasonably be attributed. So what do you think that means? Every load cell, every transducer, every instrument that walks in the door, at some point we're going to have to read it. How are we going to read it? We're going to look at the indicator, and we're going to read it by what? We're going to read it by the resolution of the instrument. So that can reasonably be attributed to the customer's device. The resolution is something that can change on various instruments submitted for calibration, and is something that we consider a short-term contributor. And then it says, where applicable, the uncertainty shall cover the same contributions to the uncertainty that were included in the evaluation of the CMC uncertainty component, except that the uncertainty components evaluated for the best existing device shall be replaced with those of the customer's device. Therefore, reported uncertainties tend to be larger than the uncertainty covered by the CMC. Yes. When you submit something, a lab, Morehouse, 0.0016%, we use the standard that's good. The uncertainties are likely going to be larger than that because we're going to have to submit this instrumentation with this resolution into the equation. And that's what they're talking about. So let's start examining things. We have resolution. I like to say resolution because people say, well, how do you calculate a load cell's resolution? Here's a very easy example. You take the capacity point or the force point, and you divide by the value at that point. You don't have to take the absolute value. It's just recommended because at some point you're going to have to do it, or you can call it negative whatever. In any case, so take the 1,000, the applied over here. We take the applied force, and then we come over here and we say, what did the load cell read at that applied force? And we look at it. So you take 1,000, take the absolute value. I recommend it because if you had compression and if you had a negative output in compression, this one has tension. I'm showing you what would happen here and why we do it, because if you would have something negative, it would pop up negative. But anyways, so we do this, we divide it. 1 millivolt then equals 481.24 pounds. From there, if we want to find the resolution, we're going to multiply by the readability. This load cell in particular reads one count at the 5th decimal place, millivolt per volt. Multiply this, and we get 0.0048 pounds. You know, in this example, we're using the uncertainty of the reference standard is listed on the scope. And here's what we were saying. The expanded uncertainty is the aggregate uncertainty of the Morehouse measurement process. That's what we did for our CMC uncertainty parameter, the Morehouse measurement process, which includes the uncertainty of the reference standard used for forced calibration and the resolution of the unit under test. So what we're adding here, we've done our repeatability studies, we've done everything else. What we're adding here is what we know, which is the resolution. That has definitely changed and is definitely one of our short-term contributors. And we're saying, and the resolution of the unit under test, it is stated with a coverage factor of k equals 2 such that the confidence interval corresponds to approximately 95%. We break this down, this whole expanded uncertainty. If we look at this, we break it down. How do we report this? What does this mean? How do we get to these numbers? UW is the maximum standard uncertainty for the calibration and measurement capability. That's our standard right here, UW. Here's our standard. We're going to multiply all these points by our uncertainty at k equals 2. We're going to reduce it, divide by 2, reduce it. And then the URes is the resolution of the force measuring instrument. And remember, we said 0.048. So we're going to use that number. And we're going to divide by the appropriate coverage factor, which is, in this case, which is the square root of 12, which is 3.464. A lot of good information on uncertainty distributions can be found in UCAS M3003. And UV then is the standard uncertainty in the calibration of the voltage ratio measurement instrumentation used at Morehouse. We were using Fluke 8508s and Agilent 3458s, 10 volt, 5 volt DC excitation, either one. And then we have complete traceability on this standard. If someone sends us an indicator with the system, then this term becomes zero because we treat everything as a system cal. Their uncertainty, when you send a complete system, the total uncertainty is a lot less. There's less to do as far as demonstrating metrological traceability, because when you do not send that indicator, now you have to make sure your indicating systems are traceable as well. So what we're doing here at the end, if those were root sum squaring, which you take the square root of UW squared plus the square root of UR squared plus the square root, and we're dividing by the along this way, dividing by the right coverage factor, k equals 2, and then URes, and dividing that by 3.6. My mouse running is lousy. So that's what we're doing. We're taking the square root of all this, and then we're going to multiply that by the right coverage factor, and then these numbers will match identically to what we have on our certificate of calibration. That's how we do the uncertainty. So when you read the certs and you see that expanded uncertainty, that's what it includes. That's the breakdown. Now we're going to discuss some load cell terms. And the first one is non-linearity, which is the algebraic difference between the output at a specified load and the corresponding point on a straight line drawn between minimum load and maximum load. This is normally expressed in units of full scale. It's common for characterization to be measured at 40 to 60%. That's what you would see on a manufacturer's spec sheet. When it says non-linearity of 0.03, it's captured somewhere between that 40 and 60%. And for non-linearity, the data is adjusted for beginning and end zero, which we're reducing both. Then the line is passed through point zero and point at capacity. Non-linearity is the difference between the output at each point and the corresponding point on the straight line. When we look at this, here's what we have over here. Here's what we have on the certificate. And when I go over here in Excel, I can do this same thing again. And on the cert, we're going to say non-linearity. We go through, what we do is we find the maximum of all the points and we report it. And if someone's astute here, they'll say 0.030029. There's just a slight bit of rounding going on there. But if we look at what's on the certificate, it's 0.115% of full scale. So we basically fit the data to a straight line right here. Non-linearity baseline, fit the data from the straight line, and then we take the difference. We take the difference between the adjusted run and the straight line, and we report that. That's all it is. And then we talking about static error band. This is the band of maximum deviations of the ascending and descending calibration points from a best fit line through zero output. It includes the effects of nonlinearity, hysteresis, and non-return to minimum load, normally expressed in units of full scale. And then for more reliable data, ascending and descending calibration information will be needed. Best fit line that passes through zero. If fit to the whole data, the data is only adjusted for the initial zero balance and not for the ending zero. So when we do this in the data here, slope, intercept, we're using something similar, an Excel function called line_est to do this. And as said here, we're going to fit it, we're going to look at it, we're going to plot the SEV baseline exactly like we were doing for nonlinearity, and then we're going to subtract the two. And in this case, the SEV was 0.119%. So that is there. Fairly easy math to do in Excel. SEV is a little bit harder than nonlinearity is really easy. Hysteresis is very easy as well. Then we're looking at coefficients. It's something else we put on our certificates and before we get to nonlinear or before we get to hysteresis. Here's coefficients. So we draw this line millivolt per volt calibration, and then we draw the best fit straight line. So if somebody were to put those millivolt values in a meter, they could expect to maybe match this. They're going to have an additional error component from the meter. This is about the best it's going to get unless they start using a higher order fit. And typically with a 10-point calibration, just drawing a straight line is good enough. And what happens here is many customers do not like want to see a zero display when you use the formula. In this situation, that is, just not how the math works. What they're going to do here is, if they want to solve for force, these are the coefficients: B0 plus B1, and then here on the output side, A0 plus A01. Really what I'm saying here is the force value, when the meter reads 0, if you plug these in and start doing the math and had a meter, right, and the meter read handles the coefficients, when it reads 0, it would actually read 0.9809753 lbf, or sometimes rounded to 0.98 lbf, as the B0 coefficient is that number as we see it there. So using math, putting this into a meter like Morehouse has, like Cellite, DSC, the PADI 4215, using the computer software that we have, going through this and using the equation, you're going to have, when you tear the meter, you're going to start at that first, this non-zero B0, because you're not going to be able to multiply that out by a 0. That's how the math works on that part. If one knows the calibration coefficients, the relationship of force versus response at very low responses, if one knows the value in millivolt per volt, they could use the formula for a straight line and then solve for, that's what we were doing in the last equation, solve for mx, y equals mx plus b, where m is the slope, x is the response, and b the y-intercept. The values are found by plotting the known force values as y and the response as x. If one knows the value for force, they could use the formula for a straight line, y equals mx plus b. The values are found by plotting the known response as y and the force values as x. So when we're giving the coefficients, all we're doing is drawing, basically using Excel, finding the slope and finding the intercept for when the force value is the x-axis and when the response value is the x. So x and y's, and we're just swapping them to get the a and b coefficients there. Hysteresis, that is defined as the algebraic difference between the output at a given load descending from maximum load and output at the same load ascending from minimum load. It's normally expressed in percentage of full scale. It is common for characterization to be measured at 40 to 60% of full scale. So you have two curves here, and you have one that's ascending and one that's descending. You're going to take the same point on these curves right here. This is the same point. The error between these, after when we plot them both, is what's reported for as hysteresis. That's all we're doing there. And here's a blown up kind of different data here. When you actually plot these, if you would do it in Excel or something else, the lines are usually straight. The errors are so small. So what we did is we did a simulation where we took these lines and amplified them by about 1,500 times what they should be to show exactly what's going on here. And you can see the output and the differences here. We have an ascending curve and a descending curve. That's what our output is. That's why this thing's going up. So in this case, you're going to plot a line for nonlinearity. That's plotted against the ascending curve, and you can see this red line right here. That would be the non-lin. And then we have SEV trying to be drawn through both curves, and then we also have hysteresis. So the hysteresis line is right here. Do it with a circle. So this is typically our descending data set. Red and red doesn't work, but that's typically this is going to be our descending line, and therefore that error, hysteresis, this other error, right here, nonlinearity, and then when we're looking at this, we can look at SEB over here. Like I said, this is amplified by 1500. I'm sure this is not clear for everyone. However, if you were to amplify it, it kind of looks, I often say this looks like a football. The ascending and descending curves of a load cell often kind of mimic that of a football. Not really, though. You can see you both halves of the football. One half is ascending, one half is descending. And if you look at the SEB, it's usually the line through the middle of that data, and then the error would be to either side. Certificates with statement of conformance. This is the new ISO standard defining decision rules. And a decision rule is defined as a rule that describes how measurement uncertainty will be accounted for when stating conformity with a specified requirement. And then we get on to section 7.13. When the customer requests a statement of conformity to a specification of a standard for test or calibration, e.g. pass fail, I want to know if my device is in tolerance, out of tolerance, I want to know if it passes, and it says clearly the specification or standard and the decision rule shall be clearly identified unless inherent in the requested specification or standard. The decision rule selected shall be communicated to and agreed with the customer. Here is an example, and this is taken, we're using the handbook and NCSLI Z540, and we're using method 5 here. But we're going to talk about this some more. We're going to talk about, we're reporting expanded uncertainty, we're reporting TUR, PFA, and then compliance rules. So, and we're doing it to method 5. Did a customer agree to that? So, are you clearly defining the decision rule with the customer? They said, are you having the discussions? Did a customer agree to method 5? I say, since it is not always possible to talk to the end user, we have produced a two-part system. That's what we do. Every quotation sent out has the following text to meet section 7.1.3. Instruments which have specified tolerance will have a guard band applied per method 5 of ANSI Z540.3 handbook. Sending an instrument in for calibration is acceptance of these terms. And then also, we try to work with all customers and offer other decision rules such as simple acceptance and method 6. Really do not want to offer simple acceptance because I don't think that meets the intent of this standard. Though if somebody wants it, standard's very clear that, the customer can overrule, good metrological practice in this case and say, give me a simple acceptance. And we strongly recommend for more reading ILAC G809 2019 for decision rules and statements of conformity. Also, there's method 2, there's root sum squared. There's a lot of different methods out there for guard banding that are acceptable. What I need to say is several organizations and publications reference or insist on maintaining a 4-to-1 test uncertainty ratio without understanding the level of risk they may be subjecting themselves to. I know this is controversial saying this to everyone. I know people reading this might say, wow, we will have the uncertainty if we maintain 4-to-1. Not always true. It's all a lot of it is dependent on that location of the measurement. And the general thought is that lab performs the calibration has standards at least 4 times better than what they've got, that everything is good. There are a lot of cases where it's not. Here's a case right here. You start seeing pass, 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 and then you see an asterisk at the bottom. The instrument has a specified tolerance of plus or minus 2 pounds of force. Does that mean that a measured value at 1,998 pounds of force out of 2,000 is in tolerance? The measurement error or bias is negative 2 pounds and is within a non-guard banded tolerance or acceptance limit. Here's where some people would say, simple acceptance, okay, we could still say pass. But there is this other standard that's gaining popularity, and it's UCAS LAB 48, and it says a rule such as simple acceptance with no account for measurement uncertainty is not an appropriate decision rule under ISO IEC 17025-2017. At best, it would be simply technically worthless, having an undefinable risk and no metrological traceability. At worst, it is misleading, using a laboratory's accreditation status to pass off a meaningless decision as something more credible than what it is. And that's true. This statement, we're not going to say pass because it has a probability of false accept of 50%. And we're going to talk about that later. And UCAS has something right to say. If you're not taking the measurement uncertainty into account, you're passing that on to the next person, the next user. How are they going to use it? Do you care how they use it? It's a discussion as a community we all need to have, because this really comes down to who absorbs, who's taking the risk. Do you want your Cal Lab to do it? At Morehouse, we're taking the risk. We're going to say we will adjust more instruments to make sure they're in tolerance and take that measurement uncertainty into account, so our customers do not have to do that. Other labs, they may not take the measurement uncertainty into account, and then you have to account for it. You have to say, hey, that lab passed that at 1998. I need this to be in tolerance. It's not good enough. You know, how do we guard band it? How do we make our measurement? You know, you're gonna have to come up with a rule. Maybe it's raise the tolerance. You know, maybe it's say, hey, when you need 2,000 pounds of force, better load that instrument so that it reads 1998 and not 2,000. So, statement of conformity. When performing a measurement and subsequent making a statement of conformity, for example, in or out of tolerance to manufacturer specification, pass, fail to a particular requirement, there are two possible outcomes. This is from the ILAC G8. The result is reported as conforming with the specification. Yay, there's much rejoicing when that happens. But that's the best thing you want to see, is something that conforms, and the result is reported as non-conforming. And here's what we're talking about. When we guard band something, here we have a band illustration of measurement decision risk. Here we have Morehouse with low uncertainties, instrument clearly in tolerance, and here we have another laboratory that maybe they don't have dead weights, they have something else, and the measurement uncertainty is much larger. And look, a lot of this hangs over the upper limit. About a third hangs in. Is it in tolerance? Is it acceptable? That's all your percent of risk. And that leads into, when we start talking not only about risk, that leads into what's deemed test uncertainty ratio. And this is the ratio of span of the tolerance of the measurement quantity subject to the calibration to twice the 95% expanded uncertainty of the measurement process used for calibration. It applies for two-sided tolerances. That's one part. It's one, TUR. So it's a UUT tolerance divided by the calibration process uncertainty. And then we have what's called the PFA, which is the probability of false accept. And the probability of false accept is defined in ANSI Z540 5.3 is tolerance type test requirement that the probability that an incorrect acceptance decision, false accept, will result from a calibration test shall not exceed 2%. With their preponderance of calibration being of this type, the resources and conditions described by the calibration procedure will require careful evaluation and determination to achieve the measurement uncertainty needed for the calibration process to achieve this allowable probability of false accept. Basically saying, hey, calculate this, and as you calculate the PFA, if anything is larger than 2%, you cannot make the conformance pass-fail or compliance pass-fail. You cannot make a statement of pass. You could make a statement of fail if it's above 2%, or you could choose to let the end user evaluate and see if it's okay or not okay. TUR, we've talked a little bit about TUR, test uncertainty ratio. That is very maintainable. However, TUR or TAR, test accuracy ratio, developed by Jerry Haynes in about the 50s and 60s with the Navy. TAR, not so much. Because what we said, hey, I want a lab that's 4 times better. And that works short term, all right? I have a process measurement that's, 1%. If we do this down here, then I need something to be 0.25% right here, right? 4 to 1. Then I need something to be 0.0125. And it just keeps going and going and getting lower and lower and higher. So at the end of the day, in this scenario, does that 1% measurement down here, is NIST really going to be, if we make it the whole way up to a National Measurement Institute, is NIST really going to be 256 times better? And is that going to be, and then if we go back to the SI, is the SI really going to be 1,000, or at the BIPM level, SI level, is it really going to be 1,024 times? It's just impossible to maintain it. In a confined system, this is very containable. If you're like, hey, we have all these instruments and all our references are 4 times better that are going to calibrate all the field instruments, and we're going to insist on that, and we're going to use primary standard laboratories to do all our calibrations, that is most likely maintainable. Though when you start trying to propagate this up, it's just not. You're not going to be 4 times better, and then 4 times better the 0125, and then 4 times better. It's just not going to happen. Not maintainable. So then we start, back into TUR, which is something that is virtually maintainable, as the uncertainty is cumulative, right? So you may start on a TUR situation, you may start with 0.1 pound, and then the next lab may be 0.15, and then 0.2, and then 0.3. And you just keep processing that uncertainty. And the TUR for that definition is UT tolerance under calibration. And typically, we're looking back to remember that ILAC P14. Remember that, the short-term contributors? This formula comes out of ANSI Z540.3 handbook. They discuss what should be in the denominator of the TUR. It's also inferred by by ILAC P14 in section 5.4. It's inferred with short-term contributors that these would be such of, at minimum, of the resolution of the UT and the repeatability of the UT. And when we do this test, right, and we look at the short terms, we're looking at a CMC, which is what's on our scope. We're looking at the resolution of what was submitted. Maybe we're looking at, additional voltage. Maybe we're looking at some other ones, but it's known error sources need to be included in here as well. And for further guidance, I suggest going to the ANSI Z54 handbook, which clearly defines the TUR denominator. When we look at this, primary lab versus, a typical force lab, or, Morehouse versus typical lab, this could be primary lab versus secondary lab. I have 2 devices here, same exact device, same exact accuracy statement, same exact resolution. Repeatability, not exactly the same. It's not going to make that much difference. The repeatability in a system, the lower my uncertainty, the better typically I can know my measurement. And the more plumb, square, rigid a machine is with low torsion, the better the repeatability. So here at Morehouse, just look at CMC of 0.002% of applied. This same load cell, 2 different labs. One lab, secondary standards, has a TUR of 1:1. That comes to Morehouse, it's 22:1. And then we get this question. Do you think a 1:1 TUR will meet ISO IEC 17025-2017, section 645, which states, the equipment used for measurement shall be capable of achieving the measurement accuracy and or measurement uncertainty required to provide a valid result? Is 1:1 good enough? Maybe it is. If you're looking to lessen your risk, 22:1 certainly sounds a whole heck of a lot better. These people may have picked up, you said guard band, method 5, guard band. The term guard band appears to have its origin in early radio days, when the band of frequencies expected to be utilized by 2 radio channel or station were separated by a band of frequency that served to guard against mutual interference by the 2 channels. Makes sense, right? You wouldn't want your bleed over. So those that remember, now everything's digital or streaming, those that remember tuning in a radio or the old knob, you kind of tune in, switch it a little bit, but you'd always have to make some type of movement. 98.5 to, the next station might have been 98.1, like a 0.4 difference. And they did this as a band, really, as the band, or AM 910, AM 980. They did this as a band to make sure you weren't, driving down listening to, Led Zeppelin, and then Hank Williams Jr. comes on, and bleeds in, and you have some really cool song that somebody should probably mix at someday or some point where you have When the Levee Breaks with TUR and whatever. So anyway, you get the point. You just didn't want that. You didn't want fighting radio stations, so they appear to have separated them. And then in ANSI Z540.3, guard bands are based on measurement uncertainty. Method 5 is the simplest guard band to calculate. The test limit is based on the worst case PFA that will be accepted for any individual measurement. Recommended for ILAC G8. High probability. The downside is that there's a very high probability of false reject because it may be too aggressive. Meaning you take the measurement uncertainty into account, and then the lab that you sent your item for calibration, they're adjusting it frequently. And the entire purpose of analyzing the PFA is to ensure your measurements are in tolerance with risk that does not exceed 2%. And why just knowing you have a 4-to-1 TUR without analyzing the PFA regarding location is not enough to minimize the measurement. Here's one where our TUR is 3.45 and our total risk is 50%. And why is that? It is because our measurement is right on the line. We could have a TUR of 20,000 to 1, and it would still be 50% if we drew that line. If we drew the curve, 50% of our data, of that curve, of that normal curve, that probability distribution would be outside of the line. So why do we care about the location of the measurement if a device is within tolerance? And then if it has a specification of 0.1% of full scale and the calibrating laboratory reports a value within 0.1, is it in tolerance, right? No, I just told everybody. The answer is, and it always will be, it depends on what the uncertainty of the measurement and what the location of the measurement is. Start looking at this in more detail. You have nominal value points. Here we're looking at 2 points in this example. We're looking at 1800 and we're looking at 2000. And here at 1800 up here, we're looking at lower specification 1798, 1802. And when we calculate the risk, it says, hey, with 2% risk or less, as long as my measurement falls between 1798.594 and 1801.406, we're good. And if I come up here, my measured value is 1799.0. That falls between the line. If you look at it up here, everything is within the tolerance limit. On the 2,000 pound point, I look at it's come down here. I've calculated this out. And based on calculating it out with 2% risk, it says as long as I fall within 1998.594 and 2001.46, I'm good. Come up here, and I'm at 1998. I need to fall between 1998.57. Therefore, right here, I am right on the line, and I have 50% risk. If this device counted by 0.1, and my device read 1998.6, we could make the statement of conformity by passing the instrument. Morehouse, here's another good example, 2,000 pound. This time, measured value is 1999. Morehouse CMC of 0.002% using primary standards. Instrument needs to read between 1998.594 right here and 2001.406, and so it was reading. You read the instrument in this case. Instrument reads 1999. We can state pass. Customer sends this to another laboratory. Their uncertainty is a bit higher than ours, right? They're using secondary standards that are 0.05%. And the instrument needs to read between 1999.186 and 2000. Lot shorter window. The other lab cannot call the force measuring instrument intolerance at 1999 since it's not within this band, so they will have to either report the asterisk or they will have to report fail. Formulas. People are saying, they're looking at this saying, well, you draw these graphs. How do you determine the 2%? Well, here's how you do it. These are Excel formulas. And you take the guard band right here. You type these in. You're going to replace lower specification limit and you're going to replace standard uncertainty. You're going to have to calculate those. You're going to have to find the lower specification limit. But if you want to draw this out or you want to do it in Excel, it's norm.inverse and the 98%. This is going to give you the, make sure it's within 2%. If you wanted to be within 3%, you put 97, and then you're going to write that formula, guard band. That's for the lower specification. Here's the one for upper specification. Lower limit risk. If you're going to calculate the risk, so now you're going to calculate the limit. That's the limit is what we saw here, right here, this line. And if you want to calculate the risk, that's this piece right here. We're going to do the lower risk, and you're going to say, you're going to write this formula here. Lower risk equals 1 minus the normal distribution measured value, and then the upper, that one. So there, those that are watching this is a real good piece. This is easy to do. Method 5, simplified. There are the formulas in Excel. Very, very easy to replicate the numbers that I have right there. So PFA, closer look. Here we use method 5. Method 5 over here. You see this is method 5. I also have method 6. And this is what this is here is a comparison of method 5 versus method 6. So sometimes people say, well, maybe it would pass with method 6. Not so much. This one, it was on the line, and being on the line, method 6 might offer, you know, a larger interval to be in, but this one did not. It was on the line. So basically throughout the one, method 5, acceptance limit 1.41, method 9, or method 6, 1.94. What that actually means is the acceptance limit is both sides. So as long as, if I use method 6, as long as I read 1998, or 19, yeah, I'm sorry, as long as I read between 1998.06 and 2001.06, I should be good. So I'm just going to I'm going to subtract the 1.94 off of, I'm going to subtract and add the 1.94. So 2001.94, if I add it, and I'm going to subtract it to 2000. So basically my limit is just that, you know, 1998.06 to 2001.94. Hopefully that makes sense. Large versus small expanded uncertainty. Here's what we're talking about. When you have a small relative span, you have much more room to be in. Look at this acceptance interval. And when, remember the primary standards at 0.002%, we look at those versus secondary at 0.01, and then you get a much smaller interval. And that's what we were just showing. So the lab with the better uncertainties, the better measurement process uncertainties, the better capabilities, is going to have a much larger acceptance interval to call your devices in tolerance. And when you think about that, what does it mean when you get a device back and it's out of tolerance? It sucks, right? You got to do root cause. You got to do, maybe you're recalling equipment. Maybe you're doing other things. Maybe you have some additional built-in tolerance. Whatever it is, it's a pain. If you get the report back and the lab says pass, you do your quality checks, you do everything else, you put it back into service and use the equipment. If it fails, it's the whole investigation process. So the measurement uncertainty is going to allow for the proper acceptance limit to be set. Anything in gray would be an acceptable location in this one. I liken this to car spots, right? The larger the TUR, the more room you have. You know, think of dead weight machine primary standards. In this situation, I can swing my door fully open. I'm not going to hit the car. I'm not going to hit another car. I could probably pull out a tailgate and even toss maybe that, football that's we're using to describe SEV, non-linearity, and hysteresis around. We do a lot of things here. And I liken this like, what are my chances to ding the other person's car door? Very, very low in this situation. The more room you have, you can swing those doors open. Versus, let's think of non-dead weight systems. Here's in a garage. Now, I want to get out of this car. I have hardly any room. If I'm carrying something, that's a pain, right? You gotta pull the stuff out. If not, I can hardly open my door, and then I have to suck it in, shimmy off, get my pants dirty, whatever I'm wearing dirty, probably unless my car's spotless and clean, and kind of shimmy out of that spot. So you decide. I mean, the lab with the smaller TURs give you less space to be in tolerance and a lot easier chance to ding the door beside you. In this example, we were, looking at the expanded uncertainty. We were looking at the uncertainty of reference standards as listed on the scope of accreditation, as well as short-term contributors for the unit under test. So what we're looking at here, and we talked about how this is reported earlier, same thing. We're going to look at resolution. We may look at repeatability. And then basically you're going to use 2 times the standard uncertainty, and which may be okay. Sometimes it gets you into trouble. I just wanted to show this because it's really worth considering, depending on how you're doing repeatability and your total combined uncertainties. Here an example. This example we're running through the Welch-Satterthwaite equation, which is recommended for the gum. And if we do this, if we look up a T-inverse formula, it is basically telling us the reference standard uncertainty and its reference resolution of the device, and is basically telling us that if our uncertainties are type, and we did a repeatability study and we took 3 measurements, it's basically telling us that the appropriate coverage factor we would need to use is not 2, but 4.303. And if we just use 2 instead of running it through this formula, we would have a difference of around 53.52% in the uncertainties. So much different. One time we're going to say the expanded uncertainty is 2.33. The other time we're going to say it's 5.02. So blindly multiplying by a coverage factor of 2 may seriously underestimate your uncertainty. Now in this case, since we're just using the resolution and the reference standard, we're not really going to have repeatability, and our degrees of freedom are going to be, since we're using combined uncertainties, our degrees of freedom are likely going to be high, and therefore multiplying by 2 would be okay. It just wanted to show this slide because it's very, very important when you're doing your uncertainties, when you're doing your repeatabilities, and you're taking the multiple measurements, that you're really considering the impact of the degrees of freedom in relation to the measurement to get the appropriate coverage factor for 95%. And just root sum squaring and multiplying everything by 2 on your level when you're doing uncertainty analysis is not going to be good enough. And if we're looking at force, typical force uncertainty for calibrations, these would be, you have equipment and you want to do calibrations for somebody else. This is what we typically would see. Type A, repeatability, non-repeatability of the reference standard, repeatability and reproducibility. These are usually done in your equipment with your machines. Then you have type B, resolution of the best existing device. We've made mention to that earlier. That's the device you really want, something awesome, maybe a second load cell, maybe a really good stable system. You can use it for statistical process control. You can use it for checks. Use it for, ILCs. You can use it if it's calibrated by dead weight. You could use it to meet some proficiency testing requirements with ILCs. In addition, so that best existing device, if you are going to do your uncertainties and need to do them, if you're calibrating in accordance with, if you're accredited and you need to do the uncertainty evaluation of uncertainty for like P14, certainly that device is going to allow you a lot of latitude and leeway to do repeatability studies, reproducibility studies, all kinds of different things and the controls. If we look at other type B contributors, reference standard resolution, if applicable. If you're using dead weight, that's 0. If you're using a load cell, you would use the reference. Reference standard uncertainty. Where was my item calibrated? Remember, this is a big one. If the reference standard uncertainty is 0.002% of applied, like at Morehouse, your uncertainty cannot be any better than this. No way. You cannot be better than the reference standard uncertainty. Reference standard stability, environmental factors, other error sources, specific. And when we look at stability, we're looking at drift. Mentioned that earlier. If you're claiming your device is good to 0.01% of full scale, whatever it is, say that's your spec, and it goes out to the lab and the lab constantly fails it, that's the time that says, hey, you don't have that stability is greater than your perceived accuracy statement, and therefore you should shorten the cal interval or raise your stability. We have guidance. It's available. This G126 is an A2LA guidance document. It will walk you through everything that is needed for not all cases, but most cases for uncertainty. Those done with in accordance with the ASTM E74, the ones that we discussed today with tolerance, the ones a load cell that are transducer with non-linearity, SEB, hysteresis, all that. We also have this spreadsheet that is a guidance document that will walk you through things as well. It's a simple Excel sheet. You just go download it, open it up, and it will show you exactly what needs to be done and how to do a proper uncertainty analysis in accordance with that G126 guidance document. So you have nice documentation, spreadsheet to back it up. Real easy to get your measurement uncertainty. And then if you want to lower that measurement risk and uncertainty, if you want to lower it, the ways to do that are use the right calibration provider and have them replicate how the device is being used. That's with the right adapters. Have competent technicians. Use the right equipment, which it would include that, those adapters, the hardness of the top locks make a difference. Pin size makes a difference. Thread engagement makes a difference. And then the big one that we can offer here is lower your risk by using a calibration provider with low uncertainties. That's the real value proposition here. We have a 5 to 7 day typical turn time. We have a 5 day turn time for special requests. Then we have standard turn time 7 to 10 business days, and we have a 2 to 3 expedite option. So we have 3 levels: 2 to 3 day, like a 5 day, and a 7 to 10. But you can, the calibration provider, using a better calibration provider will give you that ability to open that car door. Will give you the wider window for, uncertainty. Hopefully it will pass more instrumentation, so you don't have to have those product failures or the root cause or the other quality concerns that you may have when a device fails, and you might not have to issue the out of tolerance report and recall a bunch of instrumentation. Also, you using a calibration provider with a low uncertainty, maybe that allows you to lower your CMC uncertainty as well. It certainly should. So if you like this or want more, I would kindly ask anybody to subscribe to the Morehouse Insider and stay up to date on the latest industry trends, upcoming events, and calibration tips. Follow us on social media. Very active on LinkedIn. Facebook, you get the normal Facebook posts. I welcome anybody to follow us on LinkedIn. YouTube, we're posting videos. Instagram for pictures. Here's a picture of a recent new Morehouse 30,000-pound automatic deadweight machine. We have added a 30,000-pound automatic deadweight load cell calibrator to our lab to improve force calibration accuracy, also to improve our lead times. So I was struggling a little bit earlier with them, because we really shoot for, we say 7 to 10, but really shoot for 5 to 7. And the 30,000 machine expands our wide range of calibration equipment, which includes 120,000-pound, 12,000, 1,100, and 120-pound deadweight machine. So appreciate your time. It is valuable. Please feel free to email me or with any questions. Feel free to visit our website, download the recommended compression tension adapters, go to A2LA, download the guidance document G136, or go to our website and download the Excel sheet for everybody. Certainly appreciate your time. Thank you all.